Hello everyone, welcome to another video of my channel. Today I'd like to discuss on another very important and pretty much straightforward problem whose name is counting bits. At first let's get into the problem. What does it say? It says given an integer n, return an array answer of length n plus 1 such that for each I whose value will be 0 to within the range of 0 to n, the answer I is the number of ones in the binary representation of I. What does it mean? It means that we'll be given an integer whose range can be, here it is written that 0 to 100,000. We'll be given this very number. For this, we'll have to return an array whose length will be n plus 1. That means from 0 to up to that very value. In this array, what we will have to do is for each index, array has index, right? For each index, we will have to show them, or we will have to find out the number of ones, or simply saying the set bits, the number of ones in the binary representation of that index. So we will have to find this out. Here we can see some example. You see, if n is 2, what will be our output? Our output will be 0 1 1. How it is? Let's see. The very first element will be of 0 index. So 0 has no 1 in its binary representation. So for the first index we got 0. After that, here we see the binary representation of 1 is 1, so there are only one set bit, so we get 1. And also for 2, the binary representation of 2 is 1 0, so similarly 2 also has only one set bits. So this is our answer for n equals to 2. Let's see another example. Here our n, the value of n is 5, so simply let's see 3 has two ones in its binary representation. So the index 3, that is 0 1 2 3, this one. So index 3, for index 3 we get 2 is the answer. Similarly 4 has 1 1, so for index 4 we get 1, and lastly finally 5 has 2 set bits, that means 2 ones in its binary representation. So in the 5th index we get 2. Now we will have to solve it. We can solve this problem in various ways, but today I am interested only in the dynamic programming approach. So I will directly go through this approach without describing other approaches. In order to solve the problem dynamically or using dynamic programming approach, what we will have to do is find a recurrence relation. Using this recurrence relation, we'll try to find out the number of set bits for each indexes. So in order to find out the recurrence relation, maybe we need to have a closer look at the binary representations. Here in this photo we can see I have got binary representations of 1 to 60. Let's see how we can solve it. Here let us first think about the even numbers. Let's take a particular even number, say 20. In the binary representation of 20, we see it has only 2 set bits. Now let's have a look at the number that is half of 20, that is 10. In the binary representation of 10, we also have 2 set bits. Okay, let's see some more example to get a decisive conclusion. Let's see 28. 28 has 3 set bits. The half of 28 is 14. Let's see. In 14 there are also 3 set bits. We can also see, for example, 54. 54 has 4 set bits. That means 4 ones in its binary representation. What about 27? In 27 we also have 4 set bits. So from these things, from this example, can we come to a conclusion regarding the even numbers? Yes, we can. We can very well say that for any even number, the number of its set bits will be equal to half of that number. It is confirmed. So for all the even numbers, we have come to a simple conclusion that we can find the number of set bits of that even number very easily if we know the number of set bits of the half of that even number. So we got a conclusion for even numbers. Now what about odd numbers? Let us simply think one thing, that in binary representation all even numbers end with 0. All even numbers end with 0. Okay, that means the LSB or least significant bit of all even binary numbers will be 0. Similarly, that of the all odd numbers will always be 1, always end with 1. See, here the uh, LSB or least significant bits will always be 1. So we can very well say that for any even number, say x, for any even number which is x, its next odd number, that means x plus 1, will have one set bits more than it. Can't we say this? We can very well say this. This is universal truth. So can we relate this very statement with our previous conclusion of finding set bits in even numbers? Think a bit. Yes, we can. How? So we can, let's see some example. Here in 21, you see the number of set bits is 3. Its previous odd even number 20, the number of set bits was 2. So what it is in 21, it has simply one, exactly one set bits more than its previous even number. So how we can relate with our previous statement? We can relate it in such a way that for any odd number, the number of set bits will be one more than that in half of its value. By half we mean arithmetic divide. That means we will divide we will divide the odd numbers by 2 and we will truncate out the decimal part. So if we divide 21 by 2, we get 10.5. Simply truncate the zero point 0.5 and we get 10. So this will be the conclusion for finding the number of set bits in an odd number. So we got the way to find out the number of set bits in both odd and even numbers. Now let's see how we can solve it. This is our first conclusion, that says for even numbers the number of set bits in x will be equal to the number of set bits in x by 2, and for odd numbers the number of set bits in x will be equal to the number of set bits in x by 2 plus 1. Combining these two, what we get, for any number the number of set bits in x will be equals to the number of set bit in x by 2 plus the remainder of that very number, that is x by 2. This simplifies our two conclusions. If we divide any number by 2, what we get as a remainder? Either 0 or 1. If that number is even, we get 0. If that number is odd, we get 1. So this simply makes our conclusion perfect. So this is our recurrence relation. Using this recurrence relation, we will simply solve this problem. So now get to the algorithm of this our solution. Let's see. What we will do is, at first we will initialize an array or maybe vector, anything you can take, whose we will allocate it, or the array's at most value will be n plus 1, because we will have to allocate 0 also. So we will take an array whose size will be n plus 1. Next, what we will do is we will set our base condition. Here our base condition is, for 0 we do not get any set bits, so for array 0 we will simply assign it 0. This is our base condition. Using this base condition, we will gradually solve our problem gradually. That means for every index we will find out the number of set bits using this, starting from this base condition. Let's see how. Now we will simply run a loop from 1 to n. That means from the index number 1 to index number n, we will run a loop. And what we will do, we will simply apply our this recurrence relation for every index. So how can we do it? We will assign array of I to array of I divided by 2 plus I remainder by 2. So this will simply generate our number of set bits for every index. You can have a look at this very statement and think regarding this thing a bit. I hope you will understand it easily. When we are done with iterating over the loop, we will simply return the array. Thus, we can solve this counting bits problem using dynamic programming. Now it's time for implementation. Let's see how we can solve this problem in Leetcode. So guys, this is the Leetcode problem number 338, counting bits. So here we have implemented our solution using the dynamic programming approach. You can see at first we have taken a vector of size n plus 1. We have assigned its first, that means its 0 index value as 0, and for 1 to n we simply applied our recurrence relation. Now let us submit the problem and see whether we can solve it, whether we get a accepted. So we got success. Our runtime is 3 ms, faster than almost 98% of other C++ submission, and memory use is less than almost 73% of other online C++ submission. So thus we can solve the problem. I hope this video will be helpful for you guys. That's all for today. Stay fine everyone.